You know, we talk to AI models all the time. We feed them our info, we ask them our questions, but have you ever stopped to wonder what they actually remember? And what if that memory could be hacked, spilling our most private data?
I mean, really think about it. If you're using an AI that's been fine-tuned for a specific industry, like healthcare or finance, it's been trained on some seriously sensitive information. So what happens if that AI didn't just learn from your data? What if it flat out memorized it?
Well, today we're diving into some brand new research. It's so cutting edge, in fact, that it was just accepted to the super prestigious NDSS Security Symposium for 2026, and it lays out a completely new and much more powerful way to peer inside an AI's mind and see exactly what it's been holding on to.
Okay, so first things first. Let's set the stage. Why is an AI's memory such a huge deal in the first place? Well, it all comes down to its training data. You see, to get a general AI model, like Llama, to be a real expert in a specialized field, developers fine-tune it. They trained it on these smaller, highly specific datasets. We're talking patient records, confidential legal documents, proprietary financial models. You get the idea. This makes the AI an expert for sure, but it also creates a massive privacy nightmare if the model just memorizes that sensitive stuff. This is where something called a membership inference attack, or MIA, comes into play. You can think of an MIA as basically a privacy audit. It's a test designed to ask one really simple question. Hey AI, have you seen this exact piece of data before? It's our way of checking the AI's memory for secrets.
Now, we've had ways to test an AI's memory for a little while, but it turns out the old methods were fundamentally flawed. Let's break down why.
The old way of doing things was pretty intuitive. It was all based on the AI's confidence, or technically its loss score. The logic was simple. If an AI saw something in its training data, it should be a lot more confident about it when it sees it again, and give it a better score. Makes sense, right?
Well, here's the problem. Confidence is a really noisy signal. An AI might be super confident about something not because it memorized it, but just because it's a really easy question. The old attacks couldn't tell the difference between "I've seen this before" and "this is just simple." And that, as you can imagine, led to a lot of false alarms.
So the researchers behind this new paper decided to flip the script. Instead of asking how confident the AI is, they asked a much smarter question. How much more can it learn? And this brings us to the core breakthrough of their work. They found a new signal they call the optimization gap. It's based on the idea of diminishing returns. You know how when you're learning a new skill, you make huge progress at first, and then it gets harder to improve. This gap measures exactly that. How much potential to learn is left for any given piece of data. And this is the key. For a piece of data the model has never seen, a non-member, there's a huge potential to learn more about it. The optimization gap is big. But for data it has already seen and memorized during training, a member, well, it's learned just about all it can. There's very little room for improvement, so the optimization gap is tiny.
And this isn't just some abstract theory. They backed it up with hard numbers. In a controlled experiment, they found that new, unseen data had an average potential for improvement of 0.368. For memorized data, it was just 0.125. That's nearly 3 times higher for the new stuff. Now that is a clean, powerful signal. Okay, so we've got this incredibly powerful new signal. But how in the world do you measure it on a live AI that you can't just take offline and retrain? This is where the researchers came up with a brilliantly clever method. They call it in-context probing, or ICP. The amazing part is, it's a way to measure that learning potential without any training at all. It works in a black box setting, which just means you only need to be able to ask the AI questions and get answers, just like a regular user. No special access required. So how does this pop quiz work? It's genius. First, you take the data you want to test. Then, you create a probe, which is just a strategic hint. After that, you ask the AI about the data twice, once without the hint and a second time with the hint. By measuring how much that hint helped the AI's answer, you can estimate its learning potential for that data. And they even developed 2 different ways to make these hints. The first one uses similar public data as a reference, but the second strategy, which is even more powerful, doesn't need any outside data. It just cleverly modifies the original sample itself by masking out words or rewriting parts of it to create its own hint. So the big question, does this clever pop quiz actually work better than the old methods? The results are, well, they're pretty dramatic. In high-stakes situations where you absolutely cannot have a false accusation, this new attack is over 2.6 times more effective than the previous best methods. That's not a small improvement. That's a massive leap forward in our ability to spot memorized data.
And when you look at the overall performance scores, it's the same story. On a healthcare dataset, the new attack gets a score of 0.942, just crushing the old record of 0.847. It's the same deal on a news summary dataset. This new method is just consistently better, right across the board.
So what does this all mean for the future? Why does a better attack method actually matter for the rest of us?
Because this isn't just about a new way to hack AI. This is a powerful and practical tool for defense. For the first time, AI developers, auditors, and even regulators have a reliable way to test live AI systems for privacy leaks, and they can do it without needing to retrain them or have any kind of special inside access.
So, to sum it all up, the old way of checking AI memory with confidence was unreliable. This new signal, the learning potential or optimization gap, is a far more robust way to spot memorization. And this in-context probing method gives us a practical, powerful tool to finally audit an AI's memory.
This research gives us a vital new tool in the fight for AI privacy. There's no question about that. But it also leaves us with a critical question to think about. As these models get more and more capable of learning and holding on to information, can we ever be really sure our data is truly forgotten?